Welcome to this explainer. I'm absolutely thrilled you're here, because today we are taking a guided tour straight through the nervous system of modern applications. Think of me as your senior architect, and together we're going to look under the hood at how data actually moves and breathes across complex networks. If you've ever wondered how large-scale distributed systems keep all their moving parts coordinated without just, well, collapsing into total chaos, you are in exactly the right place. We're going to unpack the foundational principles of data flow, serialization, and exactly how these massive systems evolve without breaking.
Okay, let's dive right into this. Just to make sure we don't get lost in the technical weeds, we've broken today's journey into a 5-part mental scaffolding. First, defining system data flow. Then, services, REST and RPC. Third, asynchronous message passing. Number 4 is the compatibility challenge. And finally, real-world data flow in action.
Section 1. Defining system data flow. Let's start with the basics. So before we can even think about building complex, highly scalable architectures, we really need to understand how the isolated parts of a system actually talk to each other. Because, without communication, you don't really have a system at all. You just have a bunch of lonely computers. At its core, data flow is simply the movement of encoded data between different processes, services, and storage systems. As engineers, we kind of tend to think of data as static, right? Like rows sitting quietly in a database table. But in reality, data doesn't just sit there. It is constantly moving and changing shape. In memory, your data might be organized in objects or structs. But to send it over a network or write it to a disk, it has to be serialized into a self-contained sequence of bytes. Whether you're using JSON, XML, or efficient binary formats like protocol buffers, this constant translation across boundaries is literally what keeps the entire application alive. It's the true lifeblood of your architecture.
Now, what's really interesting here is how we can reframe something we do every single day. When you write data to a database, you aren't just storing it. You are fundamentally sending a message to your future self, or actually, more accurately, to a future version of your application. The process that writes the data encodes it using today's schema, but the process that reads it tomorrow might be running an entirely updated codebase. So it's basically a form of communication where the network is replaced by time and storage. And because time is passing, you have to carefully consider how your data definitions, your schemas, will evolve between the exact moment that data is written and the moment it's finally read.
Section 2. Services, REST, and RPC. Let's look at real-time communication.
But what happens when we simply can't wait for the future? What happens when two processes need to talk to each other right this second? Well, when it comes to real-time service-to-service communication, we generally see two competing philosophies. On one side, we have REST. REST is resource-based and fully embraces the messy reality of the web, leaning heavily on standard HTTP features like URLs and specific request methods. On the flip side, we have RPC, or Remote Procedure Call. Classic RPC tried to abstract the network away entirely. It attempted to make a request to a remote server look and act exactly like calling a local function in your own code. Now, modern implementations like gRPC have evolved a ton from those early days. They make network calls much more explicit and use strong binary encoding for incredible speed. But that core philosophical difference, trying to seamlessly invoke remote operations, is still there.
But here is the danger with the RPC approach. Networks are inherently chaotic. Treating a remote call like a local function is incredibly risky, because local functions are predictable. Network calls, absolutely not. You have to deal with variable latency, dropped packets, and totally unpredictable timeouts. Plus, if the client and server are written in different programming languages, you've got complex data type translations happening behind the scenes. You simply cannot ignore the network. Defensive engineering is an absolute must here. You need to rely on strategies like circuit breakers to prevent cascading failures, strict timeouts so resources aren't tied up forever, and idempotency, which is a fancy way of saying that if a network retry accidentally sends the same request twice, your system doesn't accidentally charge the user's credit card 2 times.
Section 3. Asynchronous message passing. The hybrid approach.
Okay, so databases are great for delayed communication, and APIs are built for immediate synchronous communication. But what if we need something right in the middle? Enter asynchronous message passing. This is a brilliant hybrid approach. In this system, communication goes through an intermediary. Step 1, a producer creates a message and sends it out. Step 2, an intermediary called a message broker, think of industry standards like Kafka or RabbitMQ here, receives and buffers that message. Step 3, a consumer pulls that message and processes it whenever it's ready. The real beauty here is the extreme decoupling. Producers and consumers don't even need to know about each other's existence. The broker acts as a crucial shock absorber. If the consumer crashes or gets hammered by a massive spike in traffic, no problem. The broker just safely holds on to those messages until the consumer recovers. To put that into perspective, think of it this way. A synchronous API request is kind of like being on a live phone call. If the other person puts you on hold, you're stuck waiting. You can't really do anything else. Asynchronous messaging, however, is like dropping a letter in the mail. You write the message, drop it in the mailbox, and you completely forget about it. You can immediately go back to doing other work. Now, this postal service analogy gives you incredible system resilience, but it definitely comes with a trade-off. You lose that immediate confirmation of success. You have to design your system to handle eventual consistency, basically trusting that the message broker will eventually deliver the message, even if you don't know exactly when.
Section 4. The Compatibility Challenge: How Systems Evolve.
Regardless of whether you are communicating via databases, REST, or message queues, there is one overarching tension in all data flow. It's the inescapable reality that systems evolve. Let me ask you a direct question. What happens to your application when you update your code to expect a brand new schema, but your database is still completely full of old data? We call this schema evolution. In large-scale modern environments, deploying a massive database migration that locks up your production tables for hours is completely unacceptable. Instead, we rely on rolling upgrades. This means for a significant period of time, old code and new code, old data formats and new data formats, are all going to coexist and interact within your production systems simultaneously. This makes data flow compatibility absolutely mandatory.
So, to survive this evolution without breaking everything, you have to master two types of compatibility. First up is backward compatibility. This means your brand new code might be able to seamlessly read data that was written by an older version of your code. Practically speaking, if your new code expects a new field that the old data just doesn't have, your new code has to be engineered to use sensible default values. Second, and honestly often much trickier, is forward compatibility. This means your older code, which is still running on some servers during a rolling deployment, must be able to read data written by the newer code. How do we pull that off? Well, the old code simply needs to gracefully ignore any new unrecognized fields rather than just crashing. Without strict adherence to both of these compatibility rules, your data pipelines will literally break down the second you try to deploy.
Section 5. Real-world data flow in action. Let's bring it all together.
All right, we've covered a lot of abstract concepts today. Databases, APIs, queues, compatibility. Now for the really fun part. Let's see how all of this comes together in a massive, real-world e-commerce checkout flow. Step 1. The checkout service writes the initial order to a database. Remember, that's a message to its future self. Step 2. It immediately needs to charge the user. Here, it uses a synchronous REST API call to the payment gateway. Why? Because we absolutely must have an immediate answer right now to know if the credit card clears before we confirm the order. Step 3. Once it's paid, it drops an event into an asynchronous queue for the inventory service to deduct the stock. Step 4. The notification service also reads from that exact same queue to email the customer a receipt. This is async because the user shouldn't be blocked waiting for a slow email server to respond. And finally, Step 5. Downstream, the analytics engine consumes a continuous event stream of all these actions to update the company's real-time dashboards, entirely without impacting the core transaction flow.
And this brilliantly illustrates the reality of system design today. Modern data-intensive applications are rarely just monoliths anymore. They're built as microservices. But the secret of microservices isn't really about how the individual services are split up. It is entirely about how reliably the data flows between them. They are these vibrant, sprawling ecosystems composed of dozens of specialized services, databases, and caches, all deeply and intricately connected by data flow. Reliable data flow is the actual backbone of your architecture. If the data flow stops, the whole shebang grinds to a halt.
So let's distill the core takeaways of our explainer today. Building a truly reliable system depends on three main pillars. First, you need clear data encoding and serialization formats, so systems actually understand each other and prevent translation errors. Second, you absolutely need strict forward and backward compatibility so your system can achieve zero downtime rolling upgrades. And most importantly, you have to choose the right communication pattern for the specific job. There is no single best tool. You don't use a synchronous API when you need a resilient message queue, and you don't use an async queue when you just need to instantly write state to a database.
I want to leave you with a bit of a challenge. Next time you open up your laptop, look at the codebase you're working on today. Map out the data flow.
Are your data pipelines truly resilient enough to survive a random network failure? Can they handle a massive unexpected spike in scale? Are your schemas compatible enough to survive the test of time and rolling deployments without bringing down production? Think about it. Apply these patterns we talked about and start building more robust back-end architectures. Thank you so much for joining me on this explainer, and keep engineering brilliantly.